What I thought I'd have a little look at here is hydrogen spectra and Rydberg's formula. This is really basic stuff, but again, I think I just want to keep you up to speed since we don't have much time. Hopefully you've already looked at this in the notes. So when we have a look at a hydrogen spectra, hopefully your trusty physics teacher will show you this. When you look at it through a spectroscope being a diffraction grating that's going to split up the light from the hydrogen. Obviously, if you just look at hydrogen and it hasn't been electrically excited, then you're going to get nothing. So you have it in a tube in which electricity is passed through it. The electrons gain energy, and when they fall back down, they let out light. But they do this in a very specific packets. And so when we look at the spectrum, we get a red about there, we get a blue about there, and then we get these other two up here. Indigo and violet, I suppose you call them. Indigo and violet, though I didn't really know the difference between indigo and violet, but they're at the purple end. We know that this red is around about 656.3 nanometers. The blue is around about 486.1. 434 and 410. Something like that. These are all in nanometers. It makes sense. Around about 400 for the blues, 600 for the reds. It's pretty much what we're used to. The big thing about this hydrogen spectra, obviously this is an emission spectrum. That means we're actually seeing the light. So when you look through your little spectroscope at the light coming from the hydrogen tube, which is glowing, it splits up into these red, blue and purpley bands, and we're not getting all the frequencies or wavelengths in between. We're just getting these four, and we're going, why? And what's the basis of that? And Einstein thought that it was too ridiculous to contemplate that you could actually solve for this, but we will solve for it, not in this video, but we will solve for these wavelengths, and it was Bohr that did that, Niels Bohr, possibly the only real contender for being the greatest physicist ever, apart from Newton, of course. But anyway, so we get this emission spectrum, and that means that you're actually seeing the light. There's another spectrum for the absorption spectrum. And when you take your spectroscope and look at just normal sunlight, what you're going to see is you're going to see these faint dark bands where more absorption is taking place at certain wavelengths. So this case, what we've got is more emission is taking place at certain wavelengths. That's where more absorption is taking place at more wavelengths. I might talk about that more in another video, but for now, we're just telling you what this is. So this guy, I think it was a Swiss teacher, came up with this formula. He just did it by trial and error, really. And he came up with this constant, which does have some meaning, and we'll see that. And Rydberg's constant, and it's per meter. You work it out. I think one of my classes they said, well, let's prove that that's true. So that constant gets placed in there. What does it mean? Well, it's going to give you the wavelengths of these colors. So what does the S and the L mean? Well, the S is for series, and the L is for line. And this visible spectrum is not the actual highest energy spectrum. So what we're going to find is we've got this hydrogen atom with one electron. It sort of goes around like that. And when you electrically stimulate it, it jumps up to a higher energy, and then it can fall back down. When it falls back down, and it's always this very specific amount of energy, when it falls back down, it releases energy, and we get this little wave go flying off with a very specific amount of energy. And we're going to learn that the formula that gives us that is E equals hf. So that energy difference between there and there, if we divide it by Planck's constant, we get the frequency of the photon, which of course is going to give us the wavelength. And so you can see if this basic orbit or energy level is what we call the ground state, then that is where electrons can fall back to. They can't fall any further than that. So the ones that fall back to that line, so if we were to put the energy lines, and we'll see them drawn this line, if we put that as the ground state, then that equals n equals 2, and n equals 3, etc. Then what we find is that the ones that fall back to n equals 1 give us a series. And that series is called the Lyman series. So let me just give us a bit more paper here. Let's have a look here. So let's just give us a bit more room. N equals 1, n equals 2, n equals 3, push that one up, n equals 4. And what you notice, these gaps in energy are getting smaller and smaller, and you'll be able to see why from your formula. But if we're falling back to n equals 1, so we've got 3 lines there, then in our formula, 1 over wavelength equals r times 1 over s squared minus 1 over l squared, then what we're seeing is the first series, where s equals 1. And the first line can only be the second line, where l equals 2. Alright, so we actually can't get, so if s equals 1, l equals 2 is the first line, l equals 3, l equals 4 are what we've done here. 2 down to 1, 3 down to 1, 4 down to 1. That will give you the wavelength for the light that comes out. Obviously, the one that's got the biggest energy out of these three is n equals 4 down to n equals 1. But we could do 1, so if we were to calculate that, we'd go like this. 1 over wavelength equals r, 1 over 1 squared, minus 1 over 4 squared. And we could use that to calculate our wavelength. Now, we could also come up to infinity and calculate that. Now, that would be the biggest energy that we could do. It does converge. And 1 over infinity squared is obviously 0. So we can calculate that line. This series, though, is a little higher in energy. So when s equals 1, we get this series, which we call the Lyman, and it's ultraviolet, being a little higher in energy. If we have stuff dropping down to n equals 2, like from n equals 3, n equals 4, down to n equals 2, then s equals 2, and we get what's called the Balmer. Sounds like the Obama, maybe. The Balmer series. And that's our visible guys. So those 4 lines that we looked at before, these guys, we have to use s equals 2. And so that means that we can have s equals 2, l equals 3, 4, 5, and 6. 6 down to 2 will be the highest energy one. The highest energy one will be the violet one. So we know that the red one, the lowest energy Balmer, is going to be from 3 down to 2. Alright, that's this little one here. 3 down to 2. That one there is going to be the red line. Cool. It's very cool, this stuff. I really like it. We've got another series that we talk about. Obviously, they've all got names. S equals 3. It's called the Passion. Don't know why it's called the Passion. Reminds me of Passion Tale, where all those soldiers died. But that's S equals 3. And what do you think that's going to be? Well, we went from ultraviolet, visible, down to 3, gives you infrared. And series 4 is obviously called the Stewart series. Alright, that's enough on that.